Every year, millions of kids get a vaccine to prevent a few days of itchy blisters.
Right, the classic rite of passage.
Yeah, exactly. But what if I told you that chickenpox was never actually a skin condition to begin with?
I mean, that's the big secret, really.
It totally is. The itch, the spots, the calamine lotion, it's all a decoy. Because chickenpox is incredibly deceptive.
Yeah.
It's basically this highly sophisticated neurological hitchhiker, and it permanently alters how your adult immune system functions.
Yeah, the skin rash is, well, it's essentially just a broadcast antenna for the virus.
A broadcast antenna, I love that.
Right, because the reality of what the varicella zoster virus is actually doing inside the human body, it operates on an entirely different timeline than most acute infections.
It really does.
It doesn't just, visit the host for a week and leave. It moves in for a lifetime.
Which is wild. So, welcome to today's deep dive. Our mission today is to uncover the surprising, lifelong secret life of the chickenpox virus within the human body.
It's a fascinating journey.
It really is. And to do this, we're pulling from a really interesting stack of sources. We've got the official clinical and public health guidelines from the CDC and the World Health Organization.
The heavy hitters.
Right, the heavy hitters. And we're pairing those with a detailed 2025 epidemiological paper from the journal Pathogens, authored by researcher Masayuki Nagasawa.
In synthesizing these sources, it really paints a picture of a pathogen that is brilliantly adapted to us.
Brilliantly.
I mean, humans are the only known natural host for the varicella zoster virus, or VZV.
We're it.
We are it. It has evolved exclusively alongside our biology, and because of that, it is breathtakingly contagious.
So contagious.
Yeah, the secondary attack rate, which is basically the likelihood of a susceptible person catching it after exposure, that sits between 61 and 100%.
Wow. Okay, let's unpack this, because to understand how we fight this virus, we first have to understand its incredibly stealthy invasion strategy.
Yeah, the invasion is quite a process.
So you share the same breathing air or come into direct contact with the fluid from a blister, and the cascade begins.
Right.
And in an unvaccinated person, that exposure translates to anywhere from 300 to 500 fluid-filled blisters all over the body.
But the journey from the air to the skin, that relies entirely on cellular hijacking.
Yeah, tell us about that.
So when a person inhales the viral particles, those particles absorb onto the mucosal epithelium of the airway.
Just kind of stick to the lining of the throat and lungs.
Exactly. But they don't stay in the respiratory tract. VZV immediately targets and infects specific immune cells, T cells and dendritic cells.
The immune system's own cells.
Right.
Yeah.
The virus exploits the natural function of these cells because normally dendritic cells patrol the mucosa, grab invaders, and traffic them to the regional lymph nodes to show the T cells.
Like showing them a mugshot.
Exactly. But VZV rides along deliberately.
So it's basically a fugitive hijacking the body's own police cars.
That's a great way to put it.
Instead of waiting for the immune system to hunt it down, it just climbs into the cruiser and gets a free ride straight into the lymph nodes.
Exactly. And once it's in the regional lymph nodes, it multiplies rapidly.
And that's bad news.
Yeah, this creates a primary viremia. It releases heavily infected T cells right into the bloodstream.
So the police cars are multiplying.
And they are fully compromised. Those hijacked T cells then circulate systemically. And because T cells naturally migrate to the skin to survey for damage,
Oh, wow.
yeah, the virus uses them as a direct transport vector right into the dermis. This systemic spread is the secondary viremia, and it's the biological mechanism that actually causes the blistering rash.
Which perfectly explains the timeline danger, right?
Yes, absolutely.
If the virus is using our own transit system to travel around before the skin ever breaks out, you're a walking contagion before you even know you're sick.
Who are?
You're out there shedding virus for a full 1 to 2 days before the first blister even appears.
And while the host's immune system focuses all of its energy on attacking those blisters and, forming scabs over the next 4 to 7 days.
Because that's what we see, right? The rash.
Right, but the virus is already executing the next phase of its life cycle.
It's so sneaky.
Very. At the site of every single blister, viral particles enter the microscopic sensory nerve endings in the skin.
So the skin is basically, it's merely a temporary staging ground.
It's just a pit stop.
Wait, so you're telling me chickenpox isn't a skin disease, but actually a neurological infection that just uses the skin to broadcast itself?
That is exactly what I'm telling you.
Yeah.
The actual destination is the nervous system.
That's terrifying.
And the sources note it travels retrogradely along the nerve axons. meaning it moves backward from the superficial skin, traveling up the nerve fiber until it reaches the cell body of the nerve.
All the way back to the spine.
Right, into the sensory ganglia. Specifically, places like the dorsal root ganglion sitting right outside the spinal cord.
But getting into the nervous system isn't easy, right?
No, not at all. Bypassing neural security requires a highly specialized mechanism.
Because the brain and spine are usually super protected.
Exactly. So VZV relies on a specific entry receptor called MAG.
Brag.
Right, MAG, or myelin-associated glycoprotein.
Okay, and what does MAG normally do?
Normally, MAG functions to help construct neural tissue, and it inhibits certain types of axon growth. But VZV specifically binds to this glycoprotein.
It just latches on.
It latches on, and that triggers a membrane fusion event. The viral envelope literally merges with the neuron's membrane, spilling the viral DNA directly inside.
Wow. So it's literally using our own neural construction materials as the key to slip right in.
Precisely. And once inside the nerve cell body, it establishes a lifelong latent infection.
It sets up shop forever.
Forever. But latency isn't just the virus passively falling asleep, It is an active, ongoing molecular process.
Wait, so it has to work to stay asleep?
Yes. The virus produces a specific transcript called VLT, the varicella zoster virus latency-associated transcript.
Okay, VLT.
And VLT acts as a constant silencer. It actively suppresses another viral gene called ORF61.
And let me guess, ORF61 is the trigger for replication.
You got it.
So by actively transcribing VLT to silence ORF61, the virus is physically holding down its own pause button.
What's fascinating here is how this environment ensures its survival.
Yeah, why the spine?
Well, the nervous system is an immunologically privileged site.
Meaning the immune system doesn't patrol it as hard?
Exactly. The immune system's heavily armed patrols just don't monitor these ganglia with the same aggressive inflammatory response they use elsewhere.
Why not?
Because severe inflammation in the spinal cord would cause catastrophic nerve damage.
Oh, right. That makes sense. We don't want a massive battle happening in our spinal cord.
Right. So by retreating into the nervous system, VZV finds a sanctuary where it can hide from circulating antibodies and memory T cells for decades, completely undetected.
It's a brilliant evolutionary strategy.
It really is.
But it also means that once you have the wild virus, curing it is nearly impossible. I mean, you can't scrub an entrenched virus out of your dorsal root ganglion.
No, you definitely can't.
So science had to find a way to intervene before the invasion ever happened.
Exactly. We had to beat it to the punch.
And the public health victory here is staggering. I mean, since the U.S. vaccination program began, the CDC tracks a 97% decrease in chickenpox cases.
It's an incredible success story.
Yeah, hospitalizations and deaths, which used to be a routine tragedy for thousands of healthy children, have just plummeted.
And the timeline of that medical intervention is detailed really well in the pathogens paper.
Yeah, let's go into that history.
So VZV was first isolated in 1954 by Nobel laureate Thomas Weller.
Okay, 1954.
But the real breakthrough for the vaccine didn't happen until 1971 in Japan. That's when the specific vaccine strain was isolated from a young boy named Oka.
Ah, the famous Oka strain.
Right. And developing a live, attenuated vaccine meant forcing the virus through a brutal biological gauntlet.
They really put it through the ringer.
They did. Scientists took the wild virus from the Oka child and passed it 11 times through human cells at a deliberately low temperature of 34 degrees Celsius.
That's pretty cold for the human body.
Very. And then they passed it 12 more times through fetal guinea pig cells.
Okay, so it's a freezing guinea pig boot camp.
Basically, yeah.
They locked the pathogen in a bizarre cold environment until it literally forgot how to efficiently infect a normal human.
That is pretty much what happened. Forcing the virus to replicate in those specific, non-optimal conditions triggered rapid evolutionary pressure.
Because it had to adapt or die.
Exactly. The
Yeah.
wild virus is optimized for human core body temperatures and human cellular machinery. By subjecting it to 34 degrees, which is closer to superficial skin temperature, and a non-human species barrier, it had to mutate.
Wow. And do we know exactly how it changed?
We do. The genetic sequencing of the Oka strain proves that adaptation. The resulting vaccine strain has 42 nucleotide sequence substitutions compared to the wild virus.
42 changes.
Yeah. And it is still alive. And it still presents the exact same structural proteins to the human immune system.
So our bodies still recognize it as the enemy.
Right. It triggers a robust antibody and T-cell response.
Hmm.
But those 42 genetic changes completely crippled its replication machinery.
It's like taking the engine out of the getaway car.
Yes. It simply cannot multiply fast enough to cause a systemic, blistering outbreak.
Which is a massive upgrade from relying on wild infection.
A huge upgrade.
I mean, the guidelines from both the WHO and the CDC explicitly warn against the old-school practice of chickenpox parties.
Oh, absolutely.
Intentionally exposing kids to the wild virus is a massive gamble.
It's so dangerous. Completely healthy children can suffer fatal complications from wild VZV.
Right, like pneumonia, severe bacterial skin infections, and encephalitis.
It's not something to mess around with.
Not at all. The
No.
CDC also highlights the historical danger of treating a chickenpox fever with aspirin, which can trigger Ray's syndrome.
Yeah, that was a major issue before the vaccine.
So the transition to the vaccine eliminated those acute childhood risks.
It did.
But a live, attenuated virus is still governed by its ancient biological programming.
Right, it's crippled, but it's still VZV.
It still possesses the mechanics to enter nerve endings and establish latency.
It does.
And here's where it gets really interesting, because the vaccine creates an incredible geographic quirk in the human body.
This is one of my favorite parts of the data.
It's so strange. With the wild strain, the blistering rash covers the face and the trunk of the body.
Right.
Naturally, the virus travels retrogradely from those specific blisters, ending up in the trigeminal ganglia of the face or the ganglia of the midspine.
Exactly. But the co-vaccine strain doesn't cause a diffuse full-body rash.
Right, there's no rash to travel back from.
So instead, it is administered via an intramuscular injection into a specific limb. The weakened virus enters the local nerve endings at the exact site of the injection and travels backward to establish latency.
So its permanent resting place is dictated entirely by where the needle pierces the skin. That is wild. The literal coordinates of the needle drop a pin on a map for where the virus has to sleep for the rest of the listener's life.
It's fascinating.
So if a toddler gets their shot in their upper arm, the virus travels straight to the cervical spine ganglia.
Correct.
And if they get the shot in their thigh, it anchors to the lumbar spine ganglia.
Yes, and we see evidence of this localized latency in the data on childhood shingles.
Oh, because kids can still get shingles from the vaccine.
It's very rare. There is a 79% reduction in childhood shingles compared to the wild strain.
Okay, that's a big drop.
Huge.
Yeah.
But when the okakescent does reactivate, the dermatome affected directly corresponds to the original injection site.
Wow.
Yeah, so an arm injection leads to shingles on the neck or arm. A thigh injection leads to shingles on the leg.
So even crippled, it's still an active pathogen interacting with the nervous system.
Very much so.
And the sources point out that vaccinated individuals who develop a mild breakthrough rash can still be contagious.
Yeah, there were reported cases of transmission originating from the vaccine strain.
Just from being near someone with a breakthrough rash.
Right. And in rare instances, reactivation of the Oga strain can lead to serious complications, like meningitis or acute retinal necrosis.
So it's still a real virus.
It is. Those rare complications reinforce that introducing any live virus into the human nervous system carries inherent biological variables.
It's never zero risk.
Never zero. However, the macro-level success of the Oga strain fundamentally changed the epidemiology of the virus. We essentially wiped out wild childhood chickenpox in heavily vaccinated populations.
Right. But every action in an ecosystem has a reaction.
It does.
And by eradicating wild chickenpox in kids, we accidentally created a massive immunological paradox for adults.
Yeah, this is where public health gets really complicated. The epidemiological data highlights a rising trend of shingles in adult populations.
So shingles is going up because chickenpox went down.
Essentially, yes. To understand the mechanism behind this, the pathogens paper explores the dynamic between external exposure and internal exposure.
Okay, let's talk about external exposure first.
Right. So prior to widespread vaccination in the 1990s, adult immunity was constantly maintained by environmental factors.
Because adults who survived chickenpox as kids were constantly navigating a society filled with infectious children.
Exactly. Every time an adult encountered a child shedding wild VZV at a grocery store or a school play,
They inhaled a small viral load.
they did. Now, that subclinical exposure wasn't enough to make the adult sick. Their existing antibodies neutralized the threat.
Right, they already had immunity.
But that encounter acted as a natural invisible booster shot.
Oh, wow.
Yeah, it stimulated their cellular-mediated immunity, specifically keeping their memory T cells actively engaged and highly vigilant against VZV.
So the immune system is like a muscle, and the wild virus circulating in the community was the gym.
That is a perfect analogy.
It kept those T cells swole and ready to fight.
Totally swole.
But the vaccine effectively closed the gym. Adults are no longer getting those natural external reps.
Right. If we connect this to the bigger picture, removing that external trigger means humoral immunity antibody levels slowly drops over time.
Because they're not being used.
Exactly. Cellular-mediated immunity wanes. So how does the adult immune system stay engaged at all?
That's the million-dollar question.
It relies entirely on internal exposure.
The internal battle.
Yes.
Because the virus sleeping in the dorsal root ganglion isn't dead.
Far from it.
It occasionally stops transcribing VLT, hits that ORF61 trigger we talked about, and tries to wake up.
Right. It begins localized replication. And in a healthy adult, the immune system immediately senses this localized viral activity.
It spots the jailbreak.
Exactly. It mounts a targeted response and forces the virus back into latency.
So there's a literal war happening inside our spines.
Yeah, and this silent, completely asymptomatic skirmish serves as an internal booster shot.
Without us ever feeling a thing.
Right. And the proof of this mechanism comes from incredibly unique environments. Specifically, studying astronauts during spaceflight.
Wait, astronauts?
Yes. The physiological stress of spaceflight suppresses the immune system just enough to observe this process in real time.
That is fascinating.
Scientists actually detected active varicella zoster virus shedding in the saliva of astronauts returning from space.
In their saliva. Did they have shingles?
No, they didn't have a visible shingles rash, but the silent internal battle had tipped in favor of the virus just enough for it to actively shed.
Wow, so their stressed immune systems were losing their grip on the virus.
Precisely. And as the human immune system naturally undergoes immunosenescence, which is just the weakening of immune function with age, those T cells lose their efficiency.
They get tired.
Right. So if aging adults aren't receiving external boosts from the community, and their aging immune system inevitably fails to win that silent internal skirmish.
The virus wakes up completely.
Exactly. It travels anterogradely forward down the nerve axon, back to the skin, erupting into the painful rash we know as shingles.
That is so intense. We inadvertently removed the environmental trigger that kept adult immunity strong.
We did.
So what does this all mean for public health today? If the live vaccine solved the acute danger for children, but left the aging population vulnerable to their own latent infections, modern medicine had to engineer a solution for the paradox.
And that engineering led to the recombinant subunit vaccine.
Okay, the newer shingles shot.
Right, because older adults require a massive immunological boost to prevent shingles. But immunocompromised individuals cannot safely receive a live attenuated virus.
So they couldn't just give them the Oka strain.
No, it was too risky. Scientists had to move away from using the whole pathogen.
So what did they do instead?
They isolated a specific glycoprotein from the surface of DZV and paired it with an adjuvant.
An adjuvant?
Yeah, it's a chemical agent specifically designed to provoke a massive, hyperaggressive immune response.
So it's basically a highly targeted alarm bell.
Exactly. It teaches the aging T cells exactly what to attack without the risk of an actual infection.
And does it work?
The clinical efficacy of this approach is remarkable. The WHO currently devises a 2-dose schedule of the recombinant subunit vaccine for older adults.
2 doses, okay.
And the data shows it is roughly 90% effective at preventing shingles.
90%.
And crucially, that high efficacy holds up across advanced age groups, even in individuals over 80 years old.
People whose cellular immunity has significantly waned.
Exactly. It works incredibly well.
So for everyone listening, this is the immediate practical takeaway. Check in on the vaccination status of your parents or grandparents.
Absolutely.
Because that subunit vaccine is artificially doing the heavy lifting that our wild infectious communities used to do naturally.
Exactly. And looking toward the future of viral management, the pathogens paper notes that mRNA vaccines for VZV are currently in advanced development.
Just like the COVID vaccines.
Right. By utilizing messenger RNA to instruct the host's own cells to produce the viral proteins, these vaccines are already demonstrating superior, long-lasting cellular immunity in animal models.
It's incredible to trace this life cycle. I mean, we mapped a virus that is so specialized it hijacks our own dendritic cells for a ride to the lymph nodes and uses our neural structural proteins to fuse its way into our spinal
It's
nerves.
a masterpiece of evolution.
It really is. And we looked at how scientists forced it to adapt to low temperatures to create the Okasa strain, saving countless lives but shifting the latency to the exact coordinates of the injection site.
A literal map on the body.
Yeah.
And we broke down the immunological cost of that eradication.
Yeah.
Protecting the pediatric population fundamentally altered the immune landscape for adults, requiring the development of subunit technologies to replace the natural immune boosting of the past.
It shows exactly how tightly bound our biology is to the pathogens that infect us.
We don't exist in a vacuum.
No, we don't. Which brings up a final lingering thought to explore.
Okay, let's hear it.
We know mRNA vaccines are the frontier. If mRNA technology eventually replaces the live attenuated OCA strain entirely, and the wild VZV is eradicated from the global population, humans will no longer harbor any varicella zoster virus in our dorsal root ganglions.
None at all. This raises an important question about the long-term biological baseline of our species.
Exactly. For thousands and thousands of years, this virus has quietly lived inside our nervous systems. We evolved alongside it, constantly engaged in these silent internal battles that keep our immune systems sharp.
The invisible gym?
The invisible gym. If we finally permanently evict this ancient neurological squatter for good, will our immune systems and maybe even our nervous systems function differently in its permanent absence?
Removing a lifelong passenger from the human ecosystem entirely is an unprecedented variable. We just don't know.
Something to mull over the next time you see a bottle of calamine lotion. Thank you for joining us on this deep dive. Stay curious, keep asking questions, and we'll see you next time.